In my last video, I discussed sampling distributions of sample statistics. And I want to build on that and discuss one of the, if not the most fundamentally important theorems in statistics, the central limit theorem. So let's extend on our previous ideas to populations that are not normally distributed, or populations that could have any distribution. Now, what the central limit theorem tells us is that for a population of data, regardless of the distribution, the distributions of sample means will be approximately normal. And that's if n is large enough. If n is large enough. So, how big does n have to be? Well, if the data itself is normally distributed, well, the distribution of sample means will be normally distributed regardless of the sample size. But if we don't know the distribution of the data, or we know the distribution of data is far from normal, then the standard is if sample sizes are larger than 30, then the distribution of sample means will be normal or close to normal. And if we have a fairly symmetric distribution, something close to symmetric, not normal, but symmetric, then we could relax that and say, oh, the sample size has to be bigger than 15. But like I said, if the data is normal, the distribution of the sample mean is always going to be normal. All right, so let's look at what this looks like visually. Let's say our population is up here, and that's skewed right because most of the data is on the left. But as the sample size increases, let's say if we take samples of size 2 and look at the population means, or the sample means, or samples of size 5 and look at the sample means, we might get this blue graph here, which is looking, it's getting closer to normal. But as the sample size increases, we get this red graph. And that's the distribution of X bars, of the distribution of sample means. All right, so in general, if you look at this first distribution, it's symmetric. All right, so for smaller sample sizes, the n equals 6, you get this graph that's starting to look like a normal distribution. And when you get larger sample sizes, the larger the sample size, the more normal the distribution. And so you'll see that regardless of what you start with, so up here is your original data. This is the original population. And then down here on the bottom, these are the distributions of sample means. And these are all normally distributed. And that's what the central limit theorem tells us. And then another topic I covered in the previous video on sampling distributions of statistics is that when we convert a sample statistic, when we convert a sample mean to a z-score, we use the fact that the mean of the sample means is equal to the population mean, and the standard deviation of the sample means is equal to population standard deviation divided by the square root of n. And so we have this formula for converting a sample mean to a z-score. And remember, that tells you how many standard deviations that individual sample mean is from the mean of the sample means. I know it's a little tough to follow. I'm using the word mean so many times, but that's basically what it is. All right, so let's look at an example. Suppose you have a population with a mean of 8 and a standard deviation of 3. Suppose a random sample of size n equals 36 is selected. What is the probability that the sample mean is between 7.8 and 8.2? So notice we weren't told what the distribution of the original data is, but we don't need that because the sample size is large enough that the original data could have any distribution. But since n equals 36, we could use the normal distribution as our model because we know the distribution of sample means will be normal. So we can apply the central limit theorem even if the population is not normally distributed and is larger than 30. So the mean of the sample means is equal to the population mean. We know that. And the standard deviation of the population mean, or the standard deviation of the sample means, is equal to the population standard deviation, which is given as 3, divided by the square root of the sample size, which is the square root of 36, or 6. So 3 divided by 6 is 0.5. Now, what we want to do is we want the probability that the sample mean is between these two numbers. And because we're applying the central limit theorem, we can use the normal distribution as our model for calculating the probability. So what we're basically looking for is, for the probability that x bar is between these two numbers, well, that's the same as the probability that the z-score for x bar is between these two numbers. So this is the z-score for x bar, and this is the formula for z-score. This is the z-score for x bar equals 7.8, and this is the z-score for x bar equals 8.2. Right, so we could plug 7.8 into our formula for z-score and plug 8.2 in. So this will give us negative 0.4, and this will give us positive 0.4. So to ask what is the probability that x bar is between 7.8 and 8.2 is the same as asking what is the probability that the z-score for x bar is between negative 0.4 and positive 0.4. And it's going to be equal to 0.6554 minus 0.3446. Now, where do these numbers come from? I don't want to just pull them out of thin air. So let's go over to Excel. And here's the same problem copied off of the notes. Now, what we're doing is we have our normal distribution as our model. These are z-scores, so the mean is 0. The x bar of 7.8 has a z-score of negative 0.4, and the sample mean, or x bar, of 8.2 had a z-score of positive 0.4. So here's 0.4, here's negative 0.4, and the probability that the z-scores between those two numbers is equal to the area under the normal distribution curve between those two numbers. So it's the same process. It's the same process we used with the normal distribution, standard normal distribution probability problems from a couple videos back. All right, so to find the area between these two numbers, well, Excel could only give us the area, the cumulative area all the way to the left. So what we could do is figure out first, what is the area to the left of 0.4, which is more than we need because it includes this area that we want, but it also includes this empty area over here that we don't want. So then we can subtract off that area to the left of negative 0.4, and that will leave us what we want. Okay, so this is the same process we used earlier. So we'll say equal, and I'll do this in a couple steps. So you could do it all in one cell, but I'll separate it just for the sake of this video. Equal norm.s.dist, the normal standard distribution function that if you give Excel a z-score, Excel will give you the area to the left of that z-score. So the larger z-score is 0.4, and we always use the cumulative function for continuous distribution. So yes, we'll say 1 for yes. And there's your 0.6554. Well, in the notes it was rounded to 4 decimal places, but that's where that number came from. And that's the total area. So let me switch colors here. So what we just found was all of that. That's the, in red, that's the 0.6554. And now we want to subtract off, let's use a green here. We want to subtract off the green part. So if you take all the red area minus the green area, you'll be left with the blue area in the middle, and that's what we want. And so the area to the left of negative 0.4 equal norm.s. Now remember, when you're using z-scores, you need that .s in there because the .s denotes the standard normal distribution. Norm.s.dist. And our smaller z-score is negative 0.4. And again, yes to the cumulative function. And there's where the 0.3446 came from. And so this is 0.3446. So when you subtract the 0.6554 and you take away the 0.3446, that gives you the area between z equals negative 0.4 and z equals positive 0.4. All right. So I'm going to bounce back to the notes. So this was just an explanation of where these two numbers came from. They came from the normal distribution. Okay, when we subtract them, we get 0.3108. So that is the area between the two z-scores, or the probability that the sample mean is between 7.8 and 8.2. All right, so that does it for that problem. Maybe we have one more example here we could talk about. You may want to pause the video for a